All right, good evening, everybody, and welcome to the July IGS BS session. And we're excited to have Dr. Bruce Golden and Dr. Mahdi Saatchi with us tonight to talk about an update that just went through the IGS genetic evaluation that's improving a number of growth traits, so birth weight, weaning weight, yearling weight, and milk. And so it's a real pleasure to have these two gentlemen who are heavily involved in this improvement here with us tonight to visit with you all. And before we get started, I better do my inaugural. Yeah, so we're here, it's happy hour, we're here to learn, but we're also here to have fun and to answer any questions that you have and encourage any interaction. So with that, I think we'll get started. First off will be Dr. Bruce Golden, who has a long history of working with the folks at IGS. He was the architect behind the big switch that occurred about 2 years ago when we switched to a new software called Bolt, and the methodology that software allowed for our genetic evaluation and improvements there. And we've worked really closely with Bruce before that and since that on a number of different improvements with the genetic evaluation. So we're real fortunate to have Bruce as one of our colleagues and Bruce here tonight to walk us through some of the changes that we had in growth traits that just got launched this week. So Bruce, why don't you step us through this?
Thanks, Jackie. Thanks for giving me the opportunity to cover this. I want to make a couple of points here right up front that genetic predictions are and should be a thing that are always evolving. And of course, with the advent of things like markers and genetic markers, that was a step forward that helped us to evolve. But also analytical models change over time, new techniques for how to handle different effects in models change over time as science and literature march on. And so our goal is always and should always be that we incorporate the latest and greatest developments in the field as they become available. And the goal here is there is no such thing as the perfect prediction. That these are predictions, and just like weather forecasts, predictions get better and better as analytical models and techniques improve. So what we're going to talk about here now are a series of improvements that we saw we were able to make to the growth trait analysis. We hope to incorporate additional improvements into other traits as they become available, and just keep working through these things, churning them over time. And so I want everyone to realize that there is no such thing as a perfect prediction, but there are better predictions as techniques evolve, and these are just predictions. They are just predictions. One of my friends and colleagues, Dorian Derrick, said to me one time that there is no right prediction. There are just some predictions that are better than others. And I think that's what we're experiencing here, an opportunity to improve predictions and make them better than before. We know that when we implement it, and I think Mahdi will talk a little bit about this, I think, that when we implemented the Bolt and marker effects models analyses, that we made a very large improvement in the quality of predictions. And I think the improvement that we're talking about today is a much smaller but important improvement beyond that initial implementation. Basically, the changes fall into 5 different categories. And the whole thing that really started this off is we started really looking deep into birth weight. Once we got the initial Bolt analysis rolled out a few years ago, we started looking deep into birth weight, and we noticed we had issues with it. And we thought about some ways to handle those issues. I'll talk to you a little bit about that. I think unless you're new or you've been living under a rock, I think you know what we're talking about here already. We've talked a lot about it over the last several years. And when we saw that we were going to make some changes to how we handled birth weight, we decided, well, let's make some other changes. Let's look at this issue of heterogeneous variance, and I'll talk you through what that is and see if we can better account for what we call heterogeneous variance in these analyses. And along with that, well, let's look at this whole issue of weaning contemporary groups, and are we handling them correctly? Is there a better way to handle them? Since we're going to make changes, let's look at these things. And then we also knew that our initial marker subset had a lot of good literature behind it, a lot of good research, mostly conducted by our colleague Mahdi Saatchi, and we knew it was good. But could we improve the accuracy by looking at it again and looking for a new subset of markers? Genomic markers, and we're going to do this for all the traits, and I think that should be a constantly ongoing project as new chips come out and new techniques come out, and also for different traits. We know that the genetic markers aren't the same necessarily for all traits. And then while we were at it, we said let's address this direct maternal zero genetic correlation. And we'll talk a bit about that, but let me just give you a spoiler alert right up front. Almost all other analyses use a zero correlation for direct maternal, and IGS has been using a negative 0.3, and we'll talk about why and why we made the decision to change that. So that's basically 5 different things. Let's start with the birth weight, since that drove this whole initial thing. Here's a slide that shows a contemporary group of birth weights, and you can see along the side, I don't know if you can see my pointer, along the side here on the right are birth weights, and this is what a normal birth weight contemporary group should look like. The phenotypic variance should be north of 100 squared pounds of birth weight. I've grayed out the animal IDs here. Here's the age of dam. It says sire, but those are actually age of dam classes. So that's what a normal one should look like. Here's what we started seeing in the data. We'd start seeing these implausible birth weight contemporary groups where all the animals were really tightly bunched. They all looked really good. And we just felt that was an issue. Here's another one, again, an improbable birth weight contemporary group. The animals just are too uniform and too tightly bunched. Here's another one. While it looks good, it looks reasonable. There's a 190 pounder in here. This isn't biologically possible to have contemporary groups with this kind of structure. And then, believe it or not, there's a lot of this in the data. Not a lot. I mean, there is more than you want, just people turning in standard birth weights. Then we started digging in even more, and we started realizing that when people miss calves, so here's a contemporary group, or here's a set of birth weights, not a single contemporary group. No, this is a single contemporary group. A set of birth weights, and it's a large one, where there are these fill-in values, and you can see there's a spike at 90, a spike at 85, a spike at 80, and a spike at 75. And this can happen several ways, people just rounding to the nearest 5 pounds sometimes. But I think a lot of it is people either miss the calf and so take a visual guess at it. And people are pretty good at guessing to the nearest 5 pounds, but we need more precision than that. And so I think they're filling in some kind of standard weights or best guess weights. And we were seeing that kind of thing, and that dirties up the data. Again, we saw contemporary groups that were weighed in 5 pound increments, and they're useful. It's just that the error is larger in those, so we got to handle them different. And here's a contemporary group weighed in 5 pound increments. And then again, I hope this isn't new information to most of you, but we started hearing anecdotally about a lot of folks using hoof tape instead of birth weights, and we've known that hoof tape, there's quite a bit of anecdotal experience and a little bit of literature that shows that hoof tape doesn't get the variation in birth weight that a normal birth weight group should get. So the bars in red are scale birth weights, and the bars in blue are hoof tape birth weights. And you can just see the blue is sucked more toward the average here than the red, and that just is hoof tape just doesn't capture the variation in birth weight. But we did do some research that shows that the hoof tape, though, is a good predictor of birth weight. It's a predictor not of the variation in birth weight. And so we didn't want to eliminate the hoof tape data, but we wanted to come up with a way to handle it. And we did. We've come up with a way to both identify the hoof tape and then to adjust for that heterogeneity of variation. In other words, hoof tape groups have less variation than scale weight groups, and that's called heterogeneous variance. And so there are some good techniques in the literature that we applied to account for that. We actually looked at hoof tape, or we actually looked at the birth weight data, and we found basically 12 different ways that we felt people were reporting birth weights. The first way is real scale weights, tape weights, some random stuff. There was just some people guessing in there, etc., on down to, you know, fake but single age of dam, real but single age of dam, and everything kind of in between. Some fill-in weights and real data, that sort of thing. So we used this technique to identify the data in these 12 different categories. And you can see on all contemporary group data for IGS, the blue here is real scale weights. So we estimated that 48% of all the data was real good scale weight contemporary groups, followed secondly by the orange, which is tape, or the contemporary groups that have characteristics of tape data. And then we estimated at that time that 10% of the contemporary groups on all data looked suspicious, looked like it was random weights, you know, with just filled in data. We then looked at the time, the 2018 data, that was the most recent calf crop, and it had improved quite a bit. It went from 48 to 58% of the contemporary groups. This is the groups, not the data. The contemporary groups represented real data, and the tape groups was still at about 15%, but the purely fabricated data went down to about 5% from 10%. So we have seen some improvements, but this is what kind of got us going. We said, well, let's look at this heterogeneous variance model. Let's you know, pardon the equations here, but this just shows that we adjust different categories. So we lumped these 12 categories into 4, which were real, tape, dirty, and fake. And we tried to deal with the fake data more sensibly, but we ended up just eliminating it. And we then put weights into the analysis that reflect basically it reflects the heritability of the trait. You know, if it's real data, it gets full heritability. If it's tape data, it gets full heritability, but with a reduced variation. If it's dirty data, the heritability is reduced. And if it's fake data, it's eliminated. Well, we then looked at that and we said, all right, let's look at weaning weight. We do know that there is heterogeneous variance among weaning weight. We did look to determine if there was a substantial amount of unreliable data in the weaning weight using the same techniques that we did on birth weight. And believe it or not, we didn't find a large amount. We were able to find some, but it was at such small levels and in such small specific contemporary groups that we said, it's not hurting anyone. Let's not worry about it. But we did know that sex has an effect on the variation in weaning weights. In other words, heifer calves, the variance of heifer calves is less than the variance of bull calves. And that can cause a bias in the analysis if not accounted for. So we applied that same heterogeneous variation technique to bulls versus heifers. And it turns out that bull calves, heifer calves have about 75 to 80% of the variation of a bull calf. In other words, their range or the amount that they spread is only about 75 to 80% of what bull calves do. And so by accounting for that in the analysis using this heterogeneous variance technique, we could just improve the overall prediction accuracy. So we implemented that. Then we said, well, let's just look at a new marker subset. We're making these changes. Let's see if we can improve the marker subset. And here are what we're looking at on the top line. Many of you have seen these things. They're called Manhattan plots. And this is all basically 50,000 markers on the chips that are created when you turn in a DNA sample. And each color, so the first chromosome is over here on the left, it's the red, and the second chromosome's that next blue to a third chromosome, all the way out to all the autosomes in the animal. And you can see the vertical lines, especially ones like here on the 1, 2, 3, 4, 5, 6 chromosome, you can see there's a big vertical line of markers having a major gene effect on, in this case, birth weight, but weaning weight and yearling weight all do the same thing here. And you can see others along here, markers that stick way up. In other words, some markers have a big effect. If you really hone in on this, some markers have not as big an effect and other markers have no effect at all. And in fact, we looked at this analysis and determined that, and Mahdi had already seen this in his MSRP subset study, that really the vast majority of markers for any one trait, the vast majority of these 50,000 markers have no relationship to the trait. In other words, at best, they're just noise, and at worst, they may cause an actual reduction in accuracy. But there's no point in fitting them. And so we went through an exercise that picks out the markers that are having an effect on each of the traits. So we did birth weight, weaning weight, yearling weight, all separately here. And then we combined those markers, and it turns out for each trait, there was about 1,000 to 1,500 markers for each trait that had an impact on the trait, but not all the markers were the same. In fact, only about 10 to 15% of the markers were the same for each trait, which kind of makes sense if you think about it, especially for birth weight versus the growth traits. The markers, you're talking prenatal growth in birth weight versus postnatal growth in weaning weight or yearling weight. And prenatal growth, obviously, there's not a lot of things that impact, say, feed efficiency, for example. This slide just illustrates that the correlation, in other words, the prediction accuracy of the marker subset as you add the best markers pretty much caps out for any one trait up here around 0.3533. And it caps out within the first 1,000 to 1,500 markers, and adding more markers all the way up to the maximum number of markers in the 50K set adds no prediction accuracy, adds no additional information. Here's another way to think about it. Here on the horizontal axis are effects on birth weight, marker effects on birth weight. On the vertical axis are marker effects on post-weaning gain for the same marker effects. And you can see there are a lot of markers, or a handful of markers here, that do have an effect on both traits, and those would be the ones along this axis running from -8, -8 up to 8,8. The important point about this illustration is this is a set of I don't remember what it is, 2,000 of the best markers for both traits. The vast majority of markers do not have an effect on both traits here. They have an effect on the one or the other traits. And this is the effect of birth weight markers on post-weaning gain. And so the vast majority of markers that are affecting birth weight do not affect post-weaning gain. And I think that makes sense biologically. And what that means is you really need a separate marker subset for each of the traits. And so that was the exercise we went through. We developed a marker subset for each of the traits in the analysis. Then while we're at it, so we did that. That's one of the changes in the evaluation. Then something else that we had actually known for quite a while, and I remember implementing this, I don't remember how long ago it was, 25 years ago or more, in the Red Angus evaluation. We went through an extensive study, and we realized that I mean, it's really simple. Cattlemen kind of tell you, they'll look at you and say, well, of course, different people handle calves out, especially out of 2-year-old dams, differently. Some people treat them rough. Some people supplement them. Some people put them on better pastures and take care of them. Everyone's treating them differently. Well, that is a problem. Or not everyone's treating them differently, but there are people out there treating them differently. What this plot shows you is on the horizontal axis is the age of dam. Oops, this last one is not 0. It's 11-year-old and greater. So it's calves out of 2-year-old, out of 3-year-old, out of 4-year-old, out of 5 through 10-year-old, and out of 11-year-old dams. And this is it's basically an adjustment factor. This is the effect, and this is in kilograms. This is the effect for heifers and for bulls on those age of dam effects. I think I've got that backward here. The blue is bulls and the red is heifers. And you can see that calves out of 2-year-olds weigh typically 50 pounds less at weaning than calves out of mature cows, and 3-year-olds and out of 4-year-olds. Well, what we did was we went and looked and said, is that consistent between contemporary groups? And what we saw was there were a lot of contemporary groups where this difference wasn't nearly as big as what is well known in the literature, the standard differences here. They'd be down in here, and that's a sign of preferential treatment. And it's, each of these adjustments or age of dam effects is different by different breed too, and a lot of it depends upon the average size of the breed and the group. So we knew that if this was going on, our best option for handling it was to take a contemporary group of calves, each contemporary group of calves, and divide it by calves out of 2-year-olds versus calves out of all other ages. Now, a lot of breeders automatically do that and tell us when they're giving preferential treatment. So for those breeders, there was no impact. But we still knew that or saw that there were a lot of breeders who weren't dividing it that should. This change doesn't have a huge impact except for on specific animals who get biased because of it. And so it's an important change that has very little downside. You make some smaller contemporary groups, but that's not necessarily a bad thing, especially when contemporary groups are large enough. And so we implemented that change. It's just a sensible thing to do. Then the final change that we went through, and this was debate. This has been a long-standing debate. This must be 30 years old. There are papers published in the literature, multiple papers, including papers that came out of my research group when I was at Colorado State, but a lot of others. And then Dale Van Vleck, who's one of my heroes, he's recently done a lot more work on this that shows that you were previously using about a 0.3, 0.31 negative correlation between milk, EPD, weaning milk, and weaning growth, EPD. In other words, when you were predicting it, we were saying that the more growthy animals produced less milk, and the more milk animals tend to be the smaller growth animals. And that just didn't ring true with me. It hasn't rung true with a lot of people. Some research out of my lab showed a long time ago that it was easy. So the way we come up with these correlations is we estimate them from the data. And when you estimate them from data that's not as clean, and you've seen what I mean by not as clean, these aren't research data sets, you tend to get a large negative direct maternal correlation estimate. And that original correlation estimate was estimated from field data, which has its problems. Well, that negative correlation, that estimate of the correlation is extremely sensitive to small data quality issues. It's called a negative prediction or covariance between direct and maternal. What happens is you will come up with an estimate that is negative, and it's really a result of the bias in the data and not what is in the data. So as I said earlier in my spoiler alert, virtually every other analysis in the US and elsewhere in Australia always uses a zero correlation in there. And what that does is it's not exactly saying that it is a zero. What it's saying is we start from a zero, and we don't allow that biased estimate of a correlation to drive milk negative for growthy animals. That's basically what what happens. An animal's estimate has to be based more on the performance data of its daughters, and we think that's a very sensible thing to do. And I'm really happy that IGS has adopted that philosophy on this. So that's, in a nutshell, the changes we've made. I think now Mahdi is going to talk about the impact of those changes on the quality of prediction.
Yep. 1 second. Let me make Mahdi the presenter. Thank you, Bruce. That was wonderful. And we'll have some questions to circle back with you. But I think if we want to keep rolling, we can have Mahdi do his talk and then field questions. And just as a reminder to our audience, there's a couple of ways that you can ask a question. There's a little question mark next to your name, and you can click on that and type in a question. Or there's a hand symbol next to your name, and you can click on that, and that would notify us that you have a question that you would like to ask yourself. And so we could unmute you and give you the ability to speak. So either one of those is an option. And yeah, I think we'll have Dr. Mahdi Saatchi walk us through the next step of this, which was how do we figure out if these changes are in fact an improvement. And Mahdi and others on the team did an awful lot of work to look into that with these changes that Bruce had mentioned. And Dr. Mahdi Saatchi should not be a stranger to you folks. He has worked with us for several years, and even before he was working for us, he was a postdoc at Iowa State when Dr. Dorian Garrick was there, and worked a lot with us at that time. And then we were lucky enough to recruit him. I don't know how long ago that was, Mahdi. 5 years ago, maybe? I don't know.
Yeah, about 5 years.
5 years ago, and I've really enjoyed working with Mahdi ever since. And he has recently gone on to a new arrangement where he's a consultant with IGS, and he's working full-time for himself and consulting for others as well. And so he's got a company called Top Genomics, and it's going to do big things. But it's been a pleasure to work with Mahdi, and he's brought a lot to our team. So Mahdi, why don't you walk us through the next phase of this talk?
Sure. Thank you very much, Jackie. Good evening, everyone. I hope you're enjoying your drink. Yeah, here it's a beautiful day in Iowa, but unfortunately, I cannot drink during my talk. Maybe after my talk, I take 2 drinks. Anyway, so yeah, as you hear to Dr. Golden's presentation, he walked us through all the changes that have been made to the evaluation of growth rates. And what I'm gonna do, actually, I will start with these questions that I had, or they asked me to do. I was thinking, what was my role in this venture? And I think it's more look like to the kind of inspector. Check me if this change made the prediction better and more accurate. So that's what I was thinking. I mean, the science team and the group, we had lots of meeting and discussions about, okay, we know in theory that these changes should make the EPDs more accurate and better, but how we can actually show that, how we can validate that, or how we can objectively, using some metrics, to see if we made some improvement by those proposed change and those that already implemented. So to start with that, or just giving some background, I think everybody in this call today know what it is EPD, and they use EPDs for their breeding purposes. But I want to give you another time to just go and say what do you expect from EPD. So EPD, or expected progeny difference, is basically the expectation on the future progeny performance of one bull versus the other bull. So I just give you an example here. I'm showing two bulls, bull A, red one, and bull B, the black one. And on that graph, you can see that the progeny performance could be anywhere from +3 to +60, 80, 90. As you can see, it's a kind of bell-shaped distribution, and you can see in the herd that, yeah, same bull does have different progeny performance. So once we calculate the EPDs, what we actually measure and we try to predict the future of the genetic of a bull is basically the average of the progeny performance, average based on the similar contemporary groups, similar environment, similar cow herd mates, and everything. So if the EPD for bull B show +60 versus +50 and bull A, I would expect the bull B progenies they perform 10 pound on average heavier than bull A. But that doesn't mean that every progeny of bull B should perform better. There is a variation. But if I get enough progeny out of him, I expect his calf crop are 10 pounds heavier than bull A. So you may ask, why this variation? What's the source of this variation? Why there are difference in the progeny of same bull? There are many reasons. I mean, different environment, different pasture, different contemporary groups, different cow mates. But one of the source of the variation is the bull itself. Even we calculate one EPD, that doesn't mean that genetics will, the same amount of the genetic value will pass to his progeny. I found this very good illustrative graphs from Dr. Jared Decker's University of Missouri that show or explained some of these variations among these gene pool come from same individual bull. So if you look at this, I hope my cursor show this. You look at the chromosome of this bull. He got this blue chromosome from his paternal or his sire, and this pink one from his dam. But once he generate or produce sperms, basically any combination of these 30 pairs of chromosome can be go to that one cell of this sperm, because we know only half of these chromosomes and gene goes to the sperms. That because these are random process, it could pass or it can combine differently when it packaged to the sperm. So basically, if you have it's like a looking at the coin head and tail, it many possible combination of 30 pairs of chromosomes, over 1 billion. So that's why by random process or random shuffling of genes, there's a chance that that progeny received this good set of the genes or bad set of the gene or average set of the gene. So you don't expect that every calf be similar, but if you have, as I said, enough progeny from a bull, you should have a good estimate on his average genetic merit, which is the EPD. But again, that doesn't tell the variation. And once it's come to the genomics, which is my passion about, that's exactly what the tool that we have today help us to identify or at least characterize what part of the genome or genes has been passed through the pedigree. Again, another good slide illustration from Dr. Decker. On this pedigree of the bull, you can see that this bull, he received part of his genes from his paternal grandsire and part of his gene from the maternal grandsire. But as you can see, and as I explained previously, that these genes are shuffled randomly. Once they pass to this sire or bull, it can come with different proportion. So on the pedigree side, when we don't have genomics, we try to guess that relationship, which is 50% relationship with the sire and 25% with the grandsires. But once we have genomics, we can basically look and see how much of the genes are shared between these ancestors. As in this example, for example, this bull shared 25.8% of his gene from paternal grandsire, but only 15% from his maternal grandsire. So by characterizing the exact amount of the DNA piece that has been inherited to him, we should be more accurately predict his genetic merit. So this is one way that genomics help us to refine the relationship and make the prediction more accurate. But there are other methodology, specifically the one that Dr. Bruce just showed us using the marker effect, that we can also use to improve the prediction. There are different ways of using genomics, but this approach easier to explain. But the marker effect one is basically you try to see each of those marker loci, how much they impact the trait of interest, and then again you can relate it to this same concept of amount of relationship. But I just want to give you this background of how we try to improve the prediction using different marker subset or different contemporary grouping to have a more accurate EPDs. So usually what we do, we collect phenotypes on the animals themselves and their progenies, with just for the contemporary group effects. And again, we show that we can adjust those differently. And at the end of the day, we see how much, or we rank the bulls and animals and cows by estimating their EPDs, as you can see some example here. But going to this original question that I had, and that was about those changes we implemented for work order 1 for growth rate prediction. The question was, okay, which model works better? How you can make me sure that these new EPDs are more accurate? So if the new EPDs are more accurate, they actually should predict the progeny phenotypes more accurately. That's the purpose of EPD, expected progeny difference. So what I did, or we thought the science team decided to do to compare these models, we said, okay, let's assume these individual, this calf crop doesn't have phenotype, or in other words, we mask the phenotypes in the evaluation. We assume that we don't collect these phenotypes on the calf yet. And then we said, okay, let's the models, or let the IGS evaluation goes and calculate EPDs without using those phenotypes on those set of test animals. And then, as we had the current model or old model to calculate EPDs, that one set of EPDs, and then once we implemented those changes together, and in the new updated model for growth rate, we generated a second set of EPDs on these animals that the phenotype was masked. So if the new EPDs, or second set of EPDs, are more accurate, they should be more tied to these masked phenotype, because those phenotypes have not been used. We assume they are not collected yet. We calculated EPDs, and then we try to see if they are aligned better with the phenotypes, with the real actual phenotypes, but basically adjusted for some contemporary group. So this is how we did the exercise. We excluded any phenotypes for animals that born in 2018 or later from the evaluation system. Then we ran two evaluations. One, the general production run, or the model that we had at that time. And then we ran a separate or second set of evaluation with the new changes applied. And then we compared these EPDs against those phenotypes that had not been used or masked for those test animals. And then this graph should summarize the story of what we found. On the x-axis, you see these 4 growth rate that we tested: birth, weaning, yearling, weights, and milk. And in the y-axis, you can see those correlation between EPDs we calculated for test animal and the adjusted phenotype for the contemporary group effects. And the blue bars are the old models we used to use for growth rate, and the red bars are the updated model for growth rates. And as you can see, we made improvement objectively for all the traits that we evaluated in this validation study. More improvement have been made maybe post-weaning gain, but already we made improvement for all of the traits that have been applied this change to. So that results, I think, satisfied me and the IGS team that the new proposed change helped to predict growth rate EPDs more accurately, and we have to go with it, and we did it this week, Ron. So with that, I tried to make it simple and short, give you more time to the audiences for a active discussion and questions. I think Bruce and I would be happy, and all the IGS teams would be happy to take questions and answer them. Yep. Jackie?
Yes, thank you, gentlemen. Appreciate it. And let's see, I can make you not the presenter, maybe, while I'm figuring that out.
I kind of stopped going my screen.
There you go. That's perfect. Just wanted to take a second to also introduce some of the other IGS genetic evaluation staff that's on here. And we've got Jordan Bowman is on. We've got Chip Kemp and Randy Culbertson, Dr. Culbertson, and Wade Schaefer is, I think, still chiming in, and Ryan Bolt, who you guys can see, handsome Ryan Bolt drinking a Mountain Dew there. And so there's a big team of us that work together on a variety of fronts. And so this group is here to help answer any questions that you might have. And as a reminder, if you have any questions, you can click the little question mark by your name or click the raised hand symbol by your name, and we'll get those questions taken care of for you. So in the meantime, I thought I would ask a couple of questions that I have heard. And so maybe this first one would go to Dr. Golden. Are there other traits that you think would benefit from the deep neural network system that you use to find the different patterns of different types of data coming into the system? Do you see that being applied to other traits, or is it really mainly with birth weight?
So birth weight was the obvious choice. Yeah, that's a great question, Jackie. Birth weight was the obvious choice. So there's a lot of idiosyncrasies in field data. And we don't, until now, haven't really explored or haven't really had access to a lot of tools to really look for these idiosyncrasies. I'm particularly interested in looking at stayability and looking for the way people handle different animals or the way people handle different culling policies. For stayability and for their females, and seeing if there isn't something to that can, I don't know, classify or help us to define the female fertility predictions, because they're so important. You know, that's such an important prediction, and I'd really like to be able to do that. So we've kind of scratched our head about it. I think we probably ought to devote some effort to that. I think just generally, oh, and one thing that we didn't mention here as we're doing this, did we lose Jackie, Ryan?
I think so, Bruce.
Lost? Yeah, we had a big freeze with her. Hopefully, we're all here. Anyway, I was about to say, one thing that we forgot to mention here is, since we changed birth weight and weaning weight, contemporary grouping and eliminated birth weight observations, that did have an impact on other traits in the evaluation, because we do evaluate other traits as correlated traits with birth weight and weaning weight and yearling weight. And specifically calving ease, there will be some changing in animals' calving ease because we've eliminated birth weight observations, and there will be some changes in carcass weight and carcass ribeye area because we've divided those contemporary groups. Those aren't huge changes, and we've tested them all, and they're all sensible. But just heads up, there are a couple other traits that are changing because of the change on growth traits, because we run them as correlated traits. In the future, I do think that we ought to go through. And I don't know, Mahdi, are you working on some marker subsetting for other traits? I think we ought to look at specific markers for each trait, especially now that markers are evolving. You know, in the future, we're going to see more functional markers, and we really ought to look and see what's functional on each of the traits in the evaluation. You know, this is a very complex, very large, and very extensive evaluation. So there's always opportunity to sit and explore what affects what. Mahdi, are you working on some other marker subsets right now?
Sure, yeah. Just to share that with the group, that the first marker subset we developed was based on the about 15,000 genotyped animals that was just genotyped those years. I think when I was postdoc Iowa State for 5 years ago, that was the total number of genotyped animals in the whole IGS group. So as you can see, today we have more than 250,000 genotypes in the IGS evaluations. So we start finding better markers. As we go, we get more markers with more genotype animals, as well as neo SNP chip that coming. Yeah, definitely. We always go and refine and find the better markers for the evaluation. So to just answer your question, Bruce. Yeah, I mean we are looking maybe can search for some of those functional markers on the F250 as well as using this GGP current genotype that we have for other traits. So this is ongoing project.
Super. Thanks for that, Mahdi. I'm trying to call Jackie right now and see if she's, hold on.
Yeah, I think it sounds like her internet may have dropped off, so I'll maybe just kind of follow up.
Oh, hold on. I've got two people talking in my ear. So are you going to be able to get back on, Jackie? Oh, great. Great, Ryan, you're in charge. Jackie says that she's dialing back in.
Oh, this might be a little dangerous, but we'll try our best here. You guys were just kind of recently talking about, developing different marker subsets or more optimal marker subsets for different traits. I guess what do you guys see is maybe the future or things that we could encourage, members of our different associations in terms of collecting genomic data to really try to improve the marker selection process and updating of those marker subsets? I guess maybe I'll throw that to Mahdi first, and Bruce, if you want to follow up with that, you're more than welcome to.
Mm-hmm. So I think just if you look at the technologies that coming through, probably some people heard about the low pass sequencing, a technology that enable us to get access to the massive of the data, or basically whole genome sequence data at pretty low price, which, I mean, it was very expensive before that. We just have to do it for few animals to get that. But I think with this technology becoming available in very near future, we probably can get these whole genome sequence data on every animal that we even routinely genotype for evaluation. So how many markers, how many SNPs? The current version that we just did some samples for test turn back about 59 million SNPs per individual, and comparing that to the 50,000 markers that we use today, that's a lot of change. So we have to, I mean, we have to build our enough infrastructure to store database and manage those data before we can use for routine evaluation. But I think for R&D work, I think these are good resources that help us to refine our marker subset for improving the evaluation. Yeah.
Yeah,
Bruce,
yeah, good comments, Marty. Let me follow up. So Marty's exactly right. The marker technology is going to continue to evolve. What we're really trying to do is develop markers that are closer or on the functional part of the DNA. Right now, most of the markers are near the actual functional part of the DNA, but not on the functional part of the DNA. And as these technologies improve, we're hopeful. The science is driving toward trying to get markers that actually describe the actual effect rather than something close to the actual effect on the DNA. And I don't think most people kind of realize that these markers that we've got now, the vast majority of them are only kind of an approximation, a good approximation, don't get me wrong, but we've got an opportunity to improve the accuracy of prediction as we get closer to functional markers, and the technologies Mahdi's talking about gives us an opportunity to do that because we get a lot more markers and we can start then identifying more functional work. And a lot of labs are working on functional markers. The USDA Mark and Warren Snelling in that group is one example, and they're very helpful in that area. So I think that's important. I think we will continue to evolve. It's a long, complex process. But we have to recognize that all that is an improvement in accuracy, and that's every change we make is this change that helps us increase the prediction accuracy. As we make model changes, Mahdi evaluates, did we get a prediction accuracy increase? Well, we do. As we get more functional markers, we get an anticipation of more prediction accuracy. That's what's driving all this. But there are other ways to increase prediction accuracy too, and we get so wrapped up in markers, because it is a passion, as Mahdi said. We love that stuff, and messing with the models for markers is important. One recent example that I think we're going to see results on, not to let the cat out of the bag, but there is a lot of data now is coming from dairy on beef. A lot of carcass data is coming from beef on dairy breeding, and there's a real opportunity to get a lot of high quality carcass data without genotyping. There's not a lot of motivation to genotype those animals, but one way to improve accuracy is just get a lot more data. And as you know, carcass data has been a problem. And we've recently gone through an exercise where we may be able to get as much as 50,000 new carcass records for one breed only right now, a year, just from beef on dairy. And a lot of people, Bob Weber and Matt Spangler, have been involved in validating that data and making sure that it is saying the same thing as beef on beef carcass data. And so far, all that looks very promising. So that's one example of other things that we're working on to improve the accuracy of prediction. And there are many other examples. So the ROI on that beef on dairy data is huge, right? Without genotype. And so I just want to point that out, as there are opportunities like that. Does that make sense, Ryan?
Yeah, it does. And Bruce, I think you bring up a good point there too, of, to get the most out of this genomic information, the phenotypic records are also vitally important for that process. And so it's definitely not, a mutually exclusive type thing where we can have, a bunch of genotypes and no phenotypes. We have to have as much as we can in terms of both of those things to really, boost that accuracy of prediction and find marker subsets, or even increase the accuracy of our predictions kind of overall of the population. So I think Jackie was jump.
I am back. Can you hear me?
I can, Jackie.
Excellent. Sorry, we've got a thunderstorm rolling through here, and I just lost internet there for a little bit. But we do have a question from the audience, a little hand raised here from Dr. Bert Moore. So Bert, I'm going to click your hand, and I think that will allow you to speak. Can you speak? Bert, are you able to talk? Well, that might not have worked. Let me coordinate with Kathy and see how we can get Bert mic'd up. In the meantime, we had a question about how we estimated the adjusted phenotype. And I'm assuming that's with the validation work, Mahdi, where you had the masked phenotype.
Yep.
How did you adjust those phenotypes?
Yeah, I can talk about that. So basically similar to what we are doing when we do evaluation, we adjust the raw phenotypes or raw performance data for all the known effects or contemporary group effects. So we adjusted for the contemporary group effects, sex effects, the breed or breed of dam, everything we know about have systematic non-genetic effects. So once you just do the phenotype for the contemporary group effects, then what left for you is basically genetic component. You hope what is left is genetic component plus some residual effect that you can then adjust for. So those adjusted phenotypes, again, similar to how we calculate EPDs, adjusting for all the known systematic fixed effect and contemporary groups effects. So if there is no error, then what you expect, those adjusted phenotype be exactly your EPD. So that correlation that I showed around 50 or 40% should be 100% or 1. But because we know there are some environment effect, systematic effect that we couldn't adjust for, they are part of the residual effect. That's why it's not ideal, but that allows us first thing that Bruce said, these are the predictions, means that we try to get to the ideal, but we improve and make it better, but still there are some effects that we could not adjust because we are not recording them. And yeah, so basically similar to the EPD calculations. Hope I satisfied the.
I think that worked well. And another question that we've had, but I don't know, when I got back on, it seems like maybe you folks were talking about it, but we talked about how we end up using a few thousand markers, but a lot of the genomic tests that are being done are 50,000 or 100,000 or 150,000 or more. And so could you walk us through what Bruce, you had mentioned that you add more markers and it doesn't really add more to what you know about the trait. So why would we have tests that are with so many markers, and how we end up with that smaller marker subset? And I apologize if you guys already talked about this while I was trying to get back online. So
no, we haven't talked about that, and that's a good question. And
okay.
I'll go ahead and take an initial stab at it, and then Mahdi, if you want to expand. So yeah, let me say up front, I think everyone knows that genomic testing, even though it's been around for now over a decade, and even beyond that in its most primitive form, is a very complex technology in science. And when we first developed the technology, just like 50, 70 years ago when Bloop was first developed, there was not a lot known about the actual properties of these science and technologies when we applied them. In other words, we had a lot of good theory, but then you go and put it into practice and you learn a lot. And that's absolutely true with markers. And then while we're learning these things, new markers evolve. The science identifies new potential markers and more potential markers and new ways to identify these markers and new ways to organize them. if you look at the chips available today and the chips that have been available over the last decade, there's, I don't know, Mahdi, how many are there? At least a dozen different configurations of the chips available to cattlemen alone. And now with the new rapid, genotyping by sequence technologies, these things are just changing a lot. And so what we knew, or what we thought we knew 5 years ago, is different than what we know now. We know now that they built these chips 5 years ago with their best knowledge of what might be impacting traits. And again, no single loci, no single marker necessarily impacts all traits. It doesn't necessarily impact any trait that's economically relevant to us. But you don't know that until you put it on a chip and you test it against real observations and real data. And so that's kind of the reason why we have many, many more markers. That's one of the main reasons why we have many, many more markers than we actually have markers that are telling us something. But in the future, that will improve. I mean, it's got to improve. It already has improved. Mahdi, you want to add to that?
Sure, yeah, that's my passion, so I have to talk about it. So yeah, just following on what Bruce said, Bruce, we actually have, I think last time I summarized, we had about 23 different SNP chip came in the market for cattleman. So the data I received in IGS, and there are 23 different batches, forms that I have to unify them before evaluation. Anyway, so I start with why, if we don't use all markers, why we want more. I start with some experience that the dairy producer experienced it, and other species as well, and they're still continuing doing that. And that's why when the first 50K came, I think dairy was the first one that was ahead of beef industry to apply those genomics. And then I think people said, okay, this is the accuracy, we get 50K markers. We hope that we can put more markers and more accurate. So they went and built a chip that had 700,000 markers. And there were high expectation to accuracy improves. But what it turns on the actual results of validation they didn't improve, or just 1% improve in accuracy for about 12 or even more than 12 times more markers. Why? I think, don't we have better markers in the chip 700K? Don't we have more markers closer to the genes or QTLs that should perform better? Yes, we do. But at the same time, we add much more noises or much more markers that shouldn't have effects, and we'll try to estimate their effects. So adding or going from 50,000 to 700K, add some good markers, but also add more noisy markers to the evaluation. That's why it didn't improve the predictions. So what we should do, I think we still need to get high density markers for marker discovery, because we know there are better markers in 700K, for example, but we have to identify those and just use them for the evaluation. So higher markers helping us to do R&D and identify the better markers for the evaluation. But for prediction and the practical evaluation, you need to identify a good subset of markers that are really impacting the trait, which shouldn't necessarily same marker subset for different trait. And I think Bruce mentioned earlier that based on what he's done for updating this new marker subset for growth rate, he found only 15% of markers are overlap, even for growth rates. Different set of markers are impacting. So moving from growth trait to carcass trait for stability, reproduction traits, definitely you need to have a different marker subset, which we are working on. I mean, the original MSRP subset we developed based on the limited number of genotype animals, we try to identify a set of markers that works better for all the breeds, all the traits we are evaluating. But that process now needs to be improved, and which are working on. And this work order one is one example of working on the new subset, but definitely we're working for other traits. So yeah, we for the evaluation part, we need a specific marker subset for each trait that are adding values and not adding noise. But across all traits, for R&D, we need a higher density for testing.
Excellent, thank you. Another question that we've gotten in is, so we're accepting or found a method to be able to use hoof tape as a estimate for birth weight. Can folks send in head circumference and girth as estimates of other weights, or is it really just to stick with hoof tape for the time being?
Right, yeah, good question. We do get that one a lot. So we only know the relationship of hoof tape to birth weight, or at least we only have good data to indicate the relationship between hoof tape and actual birth weights. The other measures, girth, head, anything else, we just don't have enough data to make a determination. And so if someone is willing to take those measurements and actually weigh calves, so get actual scale weights, then we can start to get a handle on it. But it really needs to be more of a design study, and it needs to be large volumes of data. So when we validated hoof tape against actual birth weights, we took several very large breeders who record data very, very well. And one of the best, I think all of you know Jimmy Butcher. I don't know if Jimmy's on here tonight, but he changed my mind on hoof tape. I was like everyone else. I was like, oh, that's bad. What, people are sending in hoof tape? Oh my gosh, that can't be good. And Jimmy went a long way to convince me, or at least Jimmy's data went a long way to convince me that, hey, we don't have a problem here. But we've got a problem in how we handle it, but it's a good indicator. So I took several large breeders who used large volumes of hoof tape, and one was Jimmy, and he knew exactly when he started using it. It was, I think, 10 years before the 2008. He said his back went out and he had to use hoof tape, and that's very pragmatic. And so we took all his data. I think there were, I don't remember, tens of thousands, over 10,000 observations on hoof tape. And we took then all the best data we could find from other breeders who had real scale weights from those same sires, and that was over 20,000 observations. And we estimated the relationship between those. And my point is, it takes a lot of data, tens of thousands of observations, to really suss these things out. So the answer is now, please don't send anything else in other than hoof tape or real scale weights. And if you do use hoof tape, please indicate that is what you have used. And the breed associations are gearing up now to try and figure out how to allow you to record, yes, I've used hoof tape. And even the Beef Improvement Federation now has embraced hoof tape. We know that we're going to get it no matter what we say. And so we definitely want to be positive about it, but definitely want to encourage people to indicate that's what they're doing. But please don't use anything else until we have better information on its relationship to birth weight. Did we lose
Gentlemen,
Jackie
I think
again?
no, I'm here. I just was muted.
Okay.
I think we're getting towards the end of the questions that have been sent in. And I guess another question I would send to both of you, since you have been so involved in big changes and innovations that have come with the IGS genetic evaluation, what do you think? What's next? What's next? What's around the corner for the folks in IGS?
I'll go ahead and start, and then Mahdi, you can talk about yours. So the immediate thing that is on the top of my plate, and there's a number of projects out there that IGS is working on, but they've asked me to take a look at mature weight and come up with the genetic predictions for mature weight. Matt Spangler and I and a postdoc we have are working on that, and we hope to have that done and a prototype out before the first of the year. Mahdi?
Yeah, and I think the other projects for novel traits that I think IGS is focusing on is the heifer pregnancy, or that I think Lane gonna lead that project with his new position at CSU. So I think these are novel traits. I think we are one adding to the profile of EPDs that IGS publish, but again, as always, we try to improve our predictions, even the small change or improvement we want to make.
Thank you, guys, and I think we're at the end of our questions. So unless I see anything else pop up here in the next few seconds, I think we'll just give you a heartfelt thank you and let everybody go on with their evening. And before we depart, I do want to emphasize that while change is scary, and if it's me and my bull and my bull's numbers just dropped because of something new that happened to the evaluation, that might not sit well with me. But the whole point of the improvements that we're putting into these to this evaluation is not just change for change's sake, but to actually do a better job of predicting. And if you're going to make model changes and you don't want it to change the system, then what's the point, right? So the whole thought of things changing and adjusting, and maybe that's good for you and maybe that's not so good for you. I have lots of empathy for the uncertainty of that. But the reality, like Bruce mentioned at the very start of this, is predictions are not perfect. And so we're constantly cranking on this system to try and improve what we're doing with the vast amount of data that's coming into the system, and try and use that data better and better and squeeze the most predictive value out of that data. And there's few people out there that have a more genuine desire to do the best that we can with that data than the two gentlemen that we had on this call tonight. So I thank you, Dr. Bruce Golden, Dr. Mahdi Saatchi, for your time and for all that you've done with our association and the genetic evaluation. I want to let everybody know on the call that we have another one of these IGS Bowl sessions set up for September, Thursday, September 24th at 5 p.m. Mountain. And that one is going to be centered around getting carcass information into a genetic evaluation and back into the hands of folks that'll use that information. And we'll have some breeders who are really committed to getting carcass records in a variety of formats. We'll have some breed association folks who help get carcass records on young sires, and we'll have some feedlot perspectives and others. So we're planning that one to not necessarily have PowerPoints and slide sets, but really be a conversation among a group of people who are really committed to carcass data and helping folks that haven't stepped into those waters know how to do that a little bit easier. So the whole goal of that session will be to really help folks that would like to enter into that know the path forward a little bit easier. So with that, gentlemen, thank you so much. Appreciate the time, and we'll sign off and talk to folks in a month.
Thank you, Jackie. Thank you, everyone.
Thanks for the opportunity.
Thanks, you guys.